Okay, this is a statistical reason. All right. Methoxy. We'll summarize later. Let's do methoxy. Who's the major product now? Para. Okay. Who do you think proceed with the fastest rate? Para. Who's the slowest rate? Meta. What does it tell you? What does this product distribution tell you about the stability of the sigma complex from the meta attack? Not that stable. Does that make sense? Let's check them out. Okay. All right. Auto attack. I'm going to go quicker this time. Show all three. Which one stabilized? Left, middle, the right? The left one. What effect? No. Not hyperconjugation. Resonance effect. Damn it. Okay. All right. Now we got some people on Zoom. Good job, people on Zoom, people. That's what I'm going to call you from now on. Hey, Zoom. You like the influencer? Hello, chat. I'm in Bahamas. Don't forget to click like, subscribe. Right? So, hello, chat. Did you do that everywhere? Or they have like the thing, like the phone thing, the stick. Thank you, the stick. You can rotate around. I'm an influencer, so come on. Don't forget to click like, subscribe. No, I'm joking. No. Okay. All right. Meta attack. What do you think compared to ortho? More stable or less stable? Less stable. Nothing there. Ew. Okay. All right. Next one. Para attack. What do you think? Which one stable? Which one? Left, middle, the right? The middle one. That one there. What effect? Yep. Okay. We're talking resonance effect. Okay. All right. Here we go. So we have, that's an ortho. That's a meta. Don't even talk about it. Meta's like out. Okay. And that's para. Now look between these two. Ortho is slower than para in this case. Well, there are two ortho, right? But why slower? Well, how big is methoxy group compared to a methyl group? Bigger or smaller? Bigger. When as big as that? Makes sense. Stereokindrins. Okay, this by having two ortho. Methyl is the only one that when you do reaction, you prefer ortho. This only one. It's gonna be as small. And methyl is the smallest alkyl group. Can you imagine that? Methyl is the smallest one. So anything beyond methyl is go to para. Okay. Oh, let's summarize it. Okay. So methoxy and methyl. Okay. Well, an alkyl group in general are ortho and para directing group. Does this term make sense? Think about this term first. What does it really mean? It's ortho and para directing group. It means that if you do electrophilic aromatic substitution, like 5 reactions you learn, when you have a methyl onto it, we have methoxy group onto it, the product will go to ortho and para. Okay, because they are ortho and para directing group. Okay, you can see that the methyl is electron donating due to the hyperconjugation, and the methoxy group is through resonance effect. Okay, they both are electron donating group, and they are ortho and para directing groups. Okay, a little bit on the side. So when you have a methoxy group, you can add bromine even without the catalyst. Benzene is activated. There's electron donating, add electron density. This benzene is much more reactive than regular benzene. Okay, methoxy benzene can react with bromine without ferric bromide, and you get 3 bromine onto benzene, ortho and para position. But you don't need to do this on exam. So on exam, they just ferric bromide as usual. Okay, all right. There are other electron donating groups. Your job is to be able to spot them. Okay, I'm going to show you. All right, start with an alkyl group. You know alkyl group, right? Carbon chain. That's it. That's all hyperconjugation people. Okay, the other one you have to be able to recognize it, the resonance one. All these guys, five these are examples. Okay, these 5 behave just like methoxy group. They donate electron to benzene. They are electron donating through resonance effect. Can you see that though? What common feature do they have just like the methoxy group? The what? The lone pair adjacent to benzene. Going to be adjacent, not too far away. Okay? Lone pair adjacent to benzene. All of them have that feature. They are electron donating through resonance effect. Look for the lone pair. Answer this question. Go. So we have ethoxy group on benzene. Is ethoxy donating or withdrawing? Donating. If ethoxy donating, it is electron, it is ortho and para directing group. Are you following? This is an ortho and para director, okay? Which means that the nitro group will go to ortho and para position like that. Oh, these two. Those are the major products. And the minor is the meta one. Which one more? I'm gonna probably guess the para. Large enough, stereokindrons around ortho. No, I'm gonna do reaction now. All right. Nitro group. The product distribution is different now. See that? Which attack proceeded with the fastest rate? Fastest rate. The meta. Okay, we're gonna explain why meta. All right, let's start with the ortho attack. Ortho attack give you these three. What do you think? Stable, unstable compared to the past. Left, middle, the right. Which one worst? The left one. Anyone can explain why this one the worst? Go for it. You guys hear that? Good job. Okay. Nitro group is electron withdrawing group. They got a positive charge. Put a positive charge next to it. Nothing can get worse than that. That's a lie. There's a much thing can get worse than that. Okay. All right. So that's instability. Okay. Look at compared to meta attack. Here's a meta. Better or worse? Better. This one better. Can you guys recognize that? Is it better? The carbocation is not directly, not adjacent to the nitro group. It's still bad, but it's not like worse than the first one, the ortho one. Okay. So, look at the para attack. What do you think? What do you think? Which one? Which one bad? Left, middle, the right? The middle one, right next to each other. Okay. So you can see that the meta attack produced the most stable intermediate or stable transition state. The fastest one. All right. Let's summarize it. Here's the nitro group. This is one of the most powerful electron withdrawing group in our class. Not like for the whole like chemistry. Okay. Just in our class. Okay. Nitro group is highly electron withdrawing for two reasons. Number one, resonance effect. Can you imagine this? This is a resonance effect. Pull electron from benzene. Okay. And number two, inductive effect. These two effects reinforces each other. Okay. So nitro group is highly electron withdrawing. Okay. So basically, ortho and para doesn't really do reacts very, very slow. Meta is the fastest one. That's why we say nitro group is a meta directing group. Does it make sense? Does it make sense? You can even think about this too. This is another way to explain, but probably easier way to explain it. Okay. When you draw the resonance structures, draw resonance structure out like that, you will see that the positive charge are on ortho and para positions. Are you following? Okay. Imagine you do electrophilic aromatic substitution, bromination, chlorination, friedel-Crafts alkylation, acylation, nitration, all those sulfonation. Okay. Those reaction is happen where benzene attacking another electrophile. Think with me. Electrophilic aromatic substitution. Benzene react with electrophile. The term electrophile. Does the electrophile have a lot of electron or less electron? Yeah, compared to nucleophile, we have the term nucleophile. That's electron density, right? Electrophile doesn't have a lot of electron. Benzene, look at ortho and para. Not much electron on ortho, para, ortho. They don't have electron there. Why would electrophile, which is electron deficient species, attack at ortho and para? There's no electron there. The highest electron density in this structure is on meta position. No charge there. No positive charge there. Does it make sense to you? Okay. All right. So nitro group is the meta directing group for that reason. Okay. Another types of not Arthur's electron withdrawing group, for example, I look right here. Okay. These two are electron withdrawing group through inductive effect. See that? Induction. A lot of electronegative atoms. Nitrogen positively charged nitrogen. What do? They take electron away from benzene. They all do the same way. Okay. I'm going to show you how slow it gets. Okay. I'm going to take, okay, let's say this is relative. Okay. Let's say a reaction on benzene. Let's set S1 as a reference. Okay. Around 6 carbon, they'll look the same. When you attach the trifluoromethyl group on benzene, all position are a million times slower. You see that? 10 to the 6th, slower than benzene. But compared between ortho and para and meta is the fastest one. This is the effect of electron withdrawing group. All positions are slower. All of them are slower because benzene has less electron density now. Okay, but in this case, meta is the fastest one among the 3 positions. Now, the following are electron withdrawing group through resonance effect, just like nitro group. Can you tell me why? How do you know? Like what gives away? The what? You have to recognize it on your own on exam. I won't be able to do on exam, so. There's not quite. All of them have two features. You're gonna have these two. One is a double bond adjacent to benzene, conjugated with benzene. Can you see that? All of them have that. Okay. Hold on before you write down. Not yet. Not just one. You can't just have a double bond like an alkene. No, alkene is electron withdrawing. Double bond adjacent to benzene, and this double bond must attach to electronegative atom. They all have the same feature. Must attach to electronegative atoms, so can pull electrons. Okay, this is resonance effect. Major product, please. So what's the major product? Ortho, meta, para. This is meta, okay? This is electron withdrawing group. This is electron withdrawing group, okay? So basically, put anything on ortho and para will be unstable. So meta is the most stable one, so the fastest reaction there, that's a product, 64%. Okay, and the rest are ortho and meta, ortho and para combined. All right, next one, we're gonna get spicy. Are you ready? 1, 2, and 3. You got to think this one. What are you going to do? Oops, lost it. Here we go. So we're adding another nitro group. What do you think this nitro group will get on benzene? Kind of hard to tell because there's no number on it, right? If there are multiple substituents on benzene, think about one at a time, okay? Let's say this benzene have only that nitro group on it. If you have just that nitro group, where the next nitro group go? The meta of it. Does that make sense? Look at the arrow, the meta of it, okay? If this benzene has only that nitro group, same thing, meta, that. You see the answer now? It's where they reinforce it, right there. That's how you think about it. Okay. All right, question on here. Well, let's summarize first. Hold on. Yeah. Let's summarize it. Okay. There are two groups on benzene. We categorize groups or substitute into two groups. That's a donating one, that's a withdrawing one. Okay. If you see a donating one, if you see a donating group will direct an incoming electrophile to what position? It's the time that you guys answer my question. You know that? Okay. Directing group, what position? Ortho and para. Okay, and we talked about why earlier. Withdrawing group is meta, directing group. Okay, usually like that. All right. Like we saw earlier, withdrawing group, you gotta keep in mind that all position on benzene is slower. When you have donating group, all position benzene is faster compared to benzene. Okay, but the fastest one is in meta position for withdrawing, and the donating one is ortho and para. Okay, now let's move to one last type of group. Okay, the third category, halogens, usually bromine and chlorine. These two, we're gonna focus on these two. Is chlorine donating or withdrawing? Guess first. Electronegativity, right? Withdrawing. If chlorine is withdrawing, what type of directing effect does it have? Meta directing group. Okay. Let's see the experimental value. Right? It makes no sense. It's magic, guys. Expecto Patronum. It's magic. Gotta ask Professor Dumbledore to explain this. It doesn't make sense. Gosh, right? So, but now let's look at this first. The experiment tell you that chlorine is an ortho and para directing group, which logically chlorine and bromine donating or withdrawing. Hold on. We're going backward. Logic, just your logic, okay? This is ortho and para directing group. Logically, chlorine should be with electron donating or electron withdrawing. Donating. We guess at the beginning, our hypothesis say, hey, this should be withdrawing because electronegativity, but the data said otherwise. See that? there are two effects that competing. I'm going to explain in a bit. Okay, there are two effects that competing. One is resonance effect, and the other is an inductive effect. Okay, let me explain this way. Oh, let me show you first. This is auto attack. The stable one is this one actually. You guys know why? This is resonance effect. See that? Next one, meta attack. This one like, yeah, nothing. And para attack, that's a good one. See that? That's a stable one. All right, this explains auto and para directing effect. Okay, this explains right here, sigma complex, the stability of sigma complex explain auto and para directing effect. So we have that now. Now, we haven't used inductive effect yet. Chlorine has a high electronegativity. Are you following on that? On a periodic table close to fluorine, right? So this is high electronegativity. What does it do? It takes away electron density from benzene. All three position, hello, although meta para attack doesn't matter, all three position is 30 times slower than benzene. So chlorine is electron withdrawing, but auto and para directing. Can you see that it doesn't really follow what we learned earlier? This guy's exception. Okay, why is it an exception? Let me explain this way. There are two effects competing. Okay, let's go back to methoxy group. We learned earlier that methoxy group is electron donating or withdrawing. Donating, auto, para, or meta directing group. Auto and para, that's what we learned before. Okay, but remember though, we haven't talked about this. Yes, this oxygen is donating through resonance effect, but it's also at the same time, it's also withdrawing through inductive effect. Are you following on that? Just like chlorine, we didn't talk about it yet because we just like, oh, that's a resonance effect. We just forgot about inductive effect. There are two effects competing, resonance effect and inductive effect. Resonance effect, adding electron, withdraw the electronic inductive effect, pulling electron away. Okay, which effect usually dominates in your experience? Resonance. This guy dominates. So that's why methoxy group is electron overall is donating. Okay. In the case of chlorine and bromine, it's different because something wrong with the resonance effect. Oh, listen carefully. Okay. Chlorine, yes, we know, inductively pulling, withdrawing, right? And also at the same time, resonance effect, donating, competing right here. Let's start with the resonance effect. Resonance effect, like the donating right here, require conjugation between p orbital and p orbital and p orbital and p orbital. You know, conjugation, p orbital next to each other, right? Tell me the size different between chlorine and oxygen. Is it chlorine and carbon? Is it the same size or different sizes? Different sizes. For this reason, the conjugation is not that effective. This is the case because it's on different row. Hold on, there's a row. Yep, different row. Oxygen and carbon, they're on the same row. Similar size. Conjugation is effective. Okay, and chlorine is not effective because of this reason. Yeah, the size is different. So resonance effect is not good. Well, inductive effect beat it. So the competition between the two. Well, para is more measured than auto. They're hindrance. Okay. All right, let's summarize the whole thing. There's a lot of things to learn right here, but I mean, if you understand it, it's not that difficult. Okay. I'm going to rank from top to the bottom. Okay. So there are a couple groups now. We have activating groups. This guy are donating group. Are you following? Activate benzene. Okay. As a result, benzene react more quickly. 25 times more, 400 times more. faster, basically, than benzene. Okay. In the activating groups, we have strong activating. The guys are strong. Why are they strong? We have resonance effect go directly to benzene. This is all donating. Okay. Next one is moderate, like in the medium activating group. How come though? Well, I'm going to take one of this. Look at this guy right there. This is, look at the lone pair. This is donating to the benzene. Can you see that? But this lone pair also conjugated with the electron withdrawing group next to it. You see that? That's why I make this guy a medium donating. Okay. So, and we have a weak one. Here's a weak one. That's hyperconjugation. Okay. All right. Hyperconjugation look like that. That's hyperconjugation. Okay. Now, the other group we call deactivating group. What does it mean? It makes benzene react more slowly. By how many times? Depends on how strong, how the strength. Okay. So we have the weak deactivating group. This guy have two effects competing. We have inductive effect pulling, okay, and the resonance effect giving away, donating. But inductive effect slightly beat resonance effect by just a little. Okay. As a result, the whole thing, like chlorine, bromine, iodine, they are weak deactivating group. Benzene slower by about 30 times, 20 times, something like that. Okay. Next one, moderate deactivating group. What they do? They're pulling electron through resonance effect. They all of them do that. Can you see that? It's the same thing, just like a nitro group. Okay. Nitro group is the strongest one because of two effects reinforce each other. We have inductive effect, the inductive effect pulling, and resonance effect also pulling away from benzene. They reinforce each other. This guy also strong as well. Lots of charges, you know, positive charge, or the positively charged nitrogen, halogens. There's a lot of them. Okay. One thing you not to be confused. Be really careful. Can you see the difference between these two? Can you see the difference between the two? One is weak deactivating group. The other is a strong deactivating group attached directly to benzene, attached to the carbon next to the benzene. Be really careful between these two. Okay. All right. Question on this? Let's just summarize basically. Yeah. Is fluorine deactivated? Is fluorine? We don't talk about fluorine because fluorine have different chemistry. If I put fluorine to the mix, that's another very confusing. Yeah, we don't do chemistry on fluorine in this course. Lots of exception. Anything I said today makes sense? Did you learn anything today? Besides, I'm also an influencer. Anything you learned? No? Okay. All right, before we go, sorry about this. I'll take you travel. If I let's do this. Look, this is kind of like the break between session. When I explain this, if I put on exam, do you think you can do that? Let's say I talk about like who let's say who is a professor at University of Berlin. Well, all right, we had Berlin last time. We go to that university. Well-known university. Anyone know? Maryland? Baltimore? Anyone have heard that name? Oh, okay. Johns Hopkins University. Okay. So, this is in 1922. Okay, way back then. Margaret Davis. What's going on, Elmer? We have found a new vitamin. It helps strengthen human bones. What is that? Vitamin? It's okay. It's okay. You know, it's fine. Okay. You know what? Yeah, that is great news. What should we name it? Let's see. Well, we discovered vitamin A 8 years ago. Vitamin B and C were discovered a year before that. That's true. How about after my last name initial, vitamin M? What about vitamin D after my initial? I want vitamin M. And I want vitamin D. How about vitamin DM? Wait, why your initial come first? What about vitamin MD? It's like parents talk about like who, like how you name like name the kids. What's the last name? Like hyphenated. What name come first? Yeah. Okay. How about rock paper scissors? That sounds very scientific, but sure. Get ready. Rock paper scissors. Shoot. Vitamin D it is. These two discover vitamin D, okay, and they publish it. Even New York Times published like right there. I copied a segment of New York Times. Okay, it's been talk of the town. Okay, the new found vitamin D. Okay, vitamin D strengthen bone, like some of you know. Okay, but how does it work? We'll talk about in a bit. Okay, all right. Meanwhile, in the University of Berlin, 1922. Where's Professor Fisher's lecture app? They don't have a phone back then. It's 1922. So it's just a map. Yeah, found it. He went to a Professor Fisher lecture. Okay, this chemistry lecture is fascinating. After the class, he went to talk to Fisher. Okay, yeah, it was an honor attending your lecture, Professor. The pleasure is mine. Can I study chemistry with you? Of course. Slay. Thank you, Professor. Here's your friend Otto Diels. Remember Otto Diels? Okay. Hi. Nice to meet you, Otto. By the way, what's your name, son? My name is Adolf. Welcome aboard, Adolf. And here's your lollipop. Would it be cool if you discover a new vitamin and got famous? Yeah, man. And you discover a new reaction and get on TV. Would it be crazy if we both won a Nobel Prize? Yeah, that's fire. Well, in 1928, Adolf won this. Wow, you guys look so disappointed for whatever reason. So disappointed, okay? He's characterized and identified, okay, use X-ray crystallography, okay, the structure of vitamin D2 and D3, okay? Vitamin D, nowadays we know it's can be produced when you absorb light, right? I'm going to explain like this. Watch closely, okay? Here's a biosynthesis of vitamin D. You don't have to take it. You just go outside to get some light, right? Here's how it works. This happens under your skin. So start from cholesterol. Do you eat cholesterol? We need cholesterol for that. That's the precursor or the starting material, basically, okay? The first step is an oxidation reaction. You don't need to know what happened there. So you get the 2 double one right there. Just that it, okay? And then we add the light onto it. Anything click? We can look just right there, just right there. What reaction are we doing? This is retro-electrocyclic reaction. Have you heard anything like that? Did you watch the video? Okay, what does light do? What does light do? Excite electron to the next level, HOMO chain. Remember that? So what's the product? Nah, that's why I'll do it. Don't matter. Okay. All right. So this is the HOMO under photochemical reaction. Look like that. Okay. You got option either these two, either one of these two. Okay. The stable one is the top one we take the top one going forward. Okay. All right. Next one is sigma-tropic rearrangement. Have you heard the term? This one 1-7 shift. You get that? Okay. All right. Look at this right here. This is a diene. Can you see this is a diene? S-cis or S-trans? This is S-cis. Go to an S-trans because it become more stable. Yeah. Okay. And this is vitamin D3. Vitamin D3 will be transported to your liver and kidney, make an active compound, and that's the strengthen your bone. See that? Okay. Read this real quick. Read. Do you know that? Don't be a lazy ass. Walk outside. You're gonna walk outside. Never be like, hey, I sit next to the sun, like in my room. No, you're gonna walk outside. Okay. All right. Last thing before we go, do you know that vitamin D is technically not a vitamin? By definition, we call vitamin, sure, right? But it's technically not a vitamin. Now the question is gonna be, what the hell is vitamin? Okay, let's look at the definition real quick. Here's a vitamin. Okay, it's by definition, it's an organic compound, essential. Okay, and cannot be synthesized. Okay, down here also another one. So organic compound, essential, cannot be synthesized. You cannot synthesize it. Can we synthesize vitamin D? We just showed you earlier there's a biosynthesis of vitamin D. It's in from your skin, goes to your liver. Okay, we can synthesize it. So the vitamin D doesn't really fit to the definition of vitamin. Okay, so if vitamin D is not a vitamin, what is it exactly? How about that? I'll see you next week.